Hey students, we're going to finish up talking about the laws that guide motion in our universe. So, as I said before, the only force that Newton actually knew about was gravity because his understanding was limited to what he could actually observe. Newton didn't have any of the technology in order to perceive the other forces in the universe. However, he could obviously observe gravity. So his observations of gravity here on Earth allowed him to create the ideas of motion. And again, that was applied through Aristotle and Galileo. So it wasn't that he came up with that completely on his own, but he was able to take those ideas and his ideas about gravity and then predict motion throughout the universe. So abiding by the four fundamental forces, all of matter on a atomic level and higher is going to follow a certain set of laws. So remember those four fundamental forces: gravity, electromagnetic force, and strong and weak nuclear forces. Again, not necessarily guiding motion on a subatomic level, but everything else. All right, and so remember in science, a law is going to be different than our legal laws, but a scientific law, a statement based on repeated experimental observations that describe the universe. So people have actually tested it multiple times. So it's not something that is at this point hypothetical. We know that, okay, this is pretty concrete. It's as close to certainty as we get in science. So this is the formula for gravity. I'm not expecting you to do any calculations, but just making sure that, hey, I'm providing you that information. All right, so this is that attractive force between all objects in the universe which possess mass. And again, when we talk about like force between the moon and the earth, that's why the earth isn't really as affected or doesn't seem as affected as the moon, because the earth has higher mass than the moon. So other laws of nature include all of these laws of nature. So these are all explained in your textbook. For this class, I'm going to talk about these laws. You will have a small activity to do on Canvas that will have you look at the other laws. All right, so we've already discussed this, the law of conservation of energy. And what that law states is that energy can transfer from being kinetic and potential as much as it wants, but the total amount of energy must always be the same. All right, so it can transfer back between being the law of motion or objects in motion, and it can be objects at rest, right? But the amount is going to stay the same. So the law of conservation of mass is very similar, but in this case, we're talking about mass. So mass can change from one form to another, but cannot be created or destroyed. So all right, so then talking about the laws of thermodynamics. So the laws of thermodynamics are talking about primarily heat, right? So it's the transfer of energy between a system and its surroundings, okay? So your body is a system. Everything around you is a surrounding. So you're transferring energy from yourself to the surroundings around you. Everything around you can also transfer energy to you. So for example, a couple different energy transformations. We can get chemical energy in the form of food, right? We transfer that energy to kinetic energy that allows us to move. The energy of the sun gets transferred to chemical energy in the plant. So the plant is able to create chlorophyll through photosynthesis, taking the light of the sun. So the first law of thermodynamics states that energy cannot be created or destroyed. It can only transfer from one object to another or change form. So basically that same principle as the law of conservation of energy. So our second law, all right, so thinking about that, if energy cannot be created or destroyed, it can be recycled, right? Unfortunately, no, that is not the case. Our energy instead will transfer from a useful form into a less useful form. So for example, a light bulb gives off light, which is useful to us, but also heat, which is less useful. And again, we're talking about useful in a form for humans. not necessarily useful in a form for other objects, right? But only for ourselves. So basically that light bulb or any system can never be 100% efficient. There will always be some loss of energy in a less useful form. So what does that mean in a practical sense? So when we're talking about heat, heat will always flow spontaneously from a higher temperature to a lower temperature, right? So we see that principle happening when we have a pot of water, of boiling water. All right, so we'll get hot water down at the very bottom of the pot. That hot water will rise because the heat will flow to where it's lower, up at the top of the pot. Then that is a little bit heavier, slower moving molecules, so that starts to sink. And as it sinks and comes down to the bottom of the pot, those molecules start to speed up again and they get hot, and then it again flows spontaneously to the lower temperature. That will create things like our convection cycle. That's really important when we talk about convection cycles in the water. It's really important when we talk about boiling water. It happens with air currents, which we'll talk about in the physical environment lecture. This is also what we see when you are holding a hot cup of coffee in your hands. The heat will spontaneously flow from the coffee cup to your hands. So in that case, maybe a little bit useful, energy efficient, but those are the laws of physics. So in our universe, we have a couple different principles, which are those principles of entropy and randomness. All right, so heat increases the randomness of the universe. Well, what does that mean? All right, you can actually see that in the image. So if our universe is orderly to start, over time we will see disorder. And it's that same thing that I just discussed, that every bit of energy that we're getting that is useful, there's also a piece that's less useful, right? That's being released as heat. So it's basically leading towards breakdown. It's sort of the same guiding principle that we see in terms of our bodies. Our body is a system, it's using energy efficiently, but parts of it are starting to break down as we age. So entropy then is a system's degree of randomness, or its degree of breakdown. So in your body, again, that might be cellular decay. In a larger system, we'll see that as maybe systems starting to break down, things of that nature. So that leads some physicists to a hypothesis about the heat death of the universe, so that all the usable energy in the universe is converted to unusable energy in the form of heat. So at the beginning of the universe, we had all of the energy that is possible present. Remember, the law of conservation of energy says that energy can transfer form as much as it wants, but the total amount will stay the same. So at the beginning of our universe, all of our energy was present. But as we move forward in time, all of that usable energy converts to unusable energy in the form of heat. So that, again, is decreasing the order in the universe, increasing the entropy in the universe. So eventually, that's the death of the universe, or what causes the universe to basically come apart. This is hypothetical. We don't know when we'd ever reach that point. Really interesting idea in physics, but again, something we're not sure about. So the third law of thermodynamics is dealing with the structure of items. In this case, we're talking about a crystal. So talking about getting absolute zero, right? If there is the crystal at perfectness, right, which would be at absolute zero, there's going to be some disorder. It's leading to eventually absolute zero, 0 Kelvin, right? At 0 Kelvin, otherwise there'll be thermal motion inside the crystal, which leads to disorder. So basically what that's saying is, if there's disorder, it cannot be absolutely perfect. It will not be at absolute zero. And again, 0 on the Kelvin scale. If there is some motion, it cannot be perfect. So let's just take a look at that link that I have posted there for you. Okay, I will post the link in our Canvas since it's not letting me open it. So moving on to talking about the gas laws. So these are two of our gas laws, Charles' law and Boyle's law. So in Charles' law, you can see in our image here, pressure is being held at a constant, temperature is increasing. So when temperature increases, the volume of our gas increases as well, but we're holding pressure at a constant. If we talk about Boyle's law, temperature is being held constant, but pressure is increasing. So when pressure increases, we see that volume decreases. So they're inversely proportionate, right? So Charles' law, when temperature increases, volume increases. Boyle's law, when pressure increases, volume decreases. And that makes sense because thinking about when we press down really hard on something, we're compressing it a lot, right? And then in our ideal gas law, we're going to combine these things. So Avogadro's law will also be combined in here. So at equal volumes of the gas at the same temperature and pressure are going to have the same number of molecules, right? So again, everything's being held constant in that particular instance. So again, when we talk about those three together, that's the ideal gas law. And we have talked about the ideal gas law before. We talked about that when we talked about the galaxy. So in this case, our pressure is being held constant and our temperature is being held constant. So you can see that volume and mass will increase. So our ideal gas law then says that if we have pressure and volume, it is equal to the number of molecules, a gas constant, and the temperature. So it's our three laws combined, Boyle's law, Charles' law, and Avogadro's law. Those three combine to make our ideal gas law. So pressure is equal to temperature times density times our constant. Pressure and volume, pressure times volume is equal to temperature times a constant. And here is our constant right here, okay? So again, I will post the links for some of our videos on Canvas. You can watch those on your own. Okay, I got our video to work, so here is our gas laws video. So that was our gas laws video, and she did a great job of explaining that for us. All right, so now we're going to talk about waves. So this is the nature of light and sound and heat. So far we've covered the energy of how objects move, which is mechanics, but we're going to talk about other types of an energy. So light does not require a medium to move, which is why light can pass freely through space. So as I think I mentioned before, when we do experiments, we can see light behave both like a wave of energy and like a particle. So it has both of those properties. Light itself has no mass. So if you recall when we watched our video about antimatter, our photons, when they're emitted, are basically their own antimatter because they have no mass. This deals with the laws of reflection and refraction. So reflection is where light will reflect off a smooth surface, like a mirror. Refraction is where our light will be scattered. For example, light on water, or you might see that on a prism. So light gets split into its different components of the visual light spectrum. So here is a video about the nature of light as both a particle and a wave. Okay, so that is our nature of light as both a particle and a wave. So, as I said, the nature of light is a little tricky. So for referring to light as a particle, we call it light, and a wave is a photon. So again, we saw that when we talked about gamma rays. They are also a photon. So in our visible light spectrum, depending on the shape or energy of the wave, the light will be a certain color or invisible altogether. So our high energy photons will appear blue. Our lower energy photons will appear red. Then outside of the visible light spectrum, things like infrared light will be a low energy photon and will be invisible. So this is our electromagnetic spectrum. I will be asking you questions about the electromagnetic spectrum on the exam. In the high frequency, high energy end of the electromagnetic spectrum, as you see, excuse me, are gamma rays. So gamma rays, if you recall, have the power to penetrate into the human body. So they are radioactive. As you move a little bit further down this end of the electromagnetic spectrum, you hit X-rays. So they're a little bit longer wavelength, so a little bit lower frequency and lower energy, but again can penetrate into the human body. Moving to the middle, this is part of the spectrum that we can see, so the visible light spectrum. As you move into the lower frequency, lower energy end of the electromagnetic spectrum, we hit things like radio waves, microwaves, and infrared light. Again, those are things that we might not see with the human eye, but they are part of the electromagnetic spectrum. So our radio waves are going to have the same energy that radio stations emit into the air, but is also emitted by other things, such as stars and gases in space. Microwaves can be used to learn about the structure of galaxies. Again, those are the same types of waves that you use to cook your food. Infrared measures heat. So as you can see, this is an infrared image of a doggo. Ultraviolet is the source of ultraviolet radiation, and the sun is our main source of that in our part of the solar system. Because it is the UV rays that cause our skin to actually burn, again, because it can penetrate into your body. Stars and other hot objects in space also emit UV radiation. So then our X-rays, are that part of the electromagnetic spectrum, are hot gases in the universe. They also emit X-rays, and we can use X-ray telescopes to perceive them. So for example, when we looked at the supernova, that was being done by the Chandra X-ray telescope. And then finally, gamma radiation, and the biggest emitter of gamma rays is actually the universe itself. So streams of photons are, of course, light. All of these move at different energy levels. Okay, so let's talk about waves. So according to dictionary.com, there are 27 different definitions of what a wave is. In science, however, a wave is a disturbance from one point to another, or a form of energy transport. So what are the characteristics of a wave? Frequency is the number of waves that pass in a given time. So typically that might be 30 seconds or a minute. So here you can also see the crest. The crest is the top of our wave. The trough is the bottom of our wave. So we would measure our wavelength, or the frequency, based on either counting the number of troughs or the number of crests. So the higher the frequency, the more energetic the wave. So our waves transport energy, not mass. And this is particular when we're talking about sound. So different types of waves that you might see. A longitudinal wave passes energy back and forth. So in motion that you might see if you had a slinky in your hands and you wiggle that back and forth, it's going to move back and forth. And you can see that in the image at the top. At the bottom, our transverse wave is more of an up and down motion. So longitudinal wave goes back and forth. Our transverse wave is up and down motion. So talking about sound, it requires a medium to conduct it. So there's that old saying that says, if you scream in space, can anyone hear you? The answer is no. And there's a bit in Star Wars, I think it's episode 8, where the ship explodes and it becomes very silent in the film. And people actually thought that the film stopped working or the sound stopped working, but actually it was because they were being dramatic, and in space you would not have heard the explosion. It would just be completely silent because it requires a medium to conduct it. In our atmosphere, molecules transfer sound. This can also go through liquids and solids. This is why you can hear sounds underwater, although they'll be muffled, as well as being able to hear sound through solids. So when you're in your car, for example, and you have a person come up next to you who's got their bass going really loud, you can hear that thumping. So sound waves are longitudinal, meaning again that the sound is moving back and forth. So just to be a little clear about the nature of these waves, so mechanical waves versus electromagnetic waves. So mechanical waves are sound, they do require a medium, and they're unable to transfer through a vacuum. Electromagnetic waves both have an electric and a magnetic nature. They are capable of traveling through a vacuum, and they do not require a medium to transport their energy. Very briefly about heat. Heat is the thermal energy content of a substance. So if they're in a higher energy state, as we've already seen before, they're going to be moving around more quickly, which means they'll be at a higher temperature. If they're at a lower temperature, there'll be lower movement of their molecules. So three different types of heat transfer: convection, conduction, and radiation. So convection, we've already discussed. This is where we have hotter, faster moving molecules at the bottom of an object or in a heat source. They will then flow spontaneously to the lower heat source or the lower energy, and then they will sink because they become heavier and slower, and then that process starts over again. So we see convection cycles in the ocean, we see convection cycles in the air. We'll see that same process happen when you boil a pot of water. Conduction is the passage of heat through the particles of a solid. So we'll see that on a pot handle. You see that when you touch your coffee cup, or as you see in the bottom graphic where the guy is grabbing the poker for the fireplace and he's burned his hand. Heat has passed through the solid particles, so the particles of the solid, excuse me, and now it's transferring heat to another object, in this case, your hand. And radiation is the passage of heat through a space. So you'll feel that when you are putting your hands to a fire, you can feel heat radiating from the fire. As you can see in the image, there's heat coming from the heater. You'll feel heat coming from the sun. So those are our three types of heat: convection, conduction, and radiation. So how do we measure heat? As I said before, there are three scales of measurement: Fahrenheit, Celsius, and Kelvin. So you might think about the different types of scales as useful in particular situations. So I've heard Fahrenheit being described as a scale that makes most sense when you're talking about living things. So we are, typically thinking of, all right, 0 degrees, really cold, right? Below the freezing point of water. So we know that there could be snow possibly. When you go to 134 degrees Fahrenheit, the highest ever recorded temperature in the United States, it's really hot. But at that point, you're really going to have issues of sustaining human life. The boiling point of water, okay, we're boiling off our skin, right? When we talk about Celsius, though, it makes the most sense when we talk about water. 0 degrees Celsius, freezing point of water. 100 degrees Celsius, boiling point of water. That very much makes sense when you're talking about water. Then Kelvin makes the most sense when you're dealing with extremes of temperature, especially very cold temperatures. So 0 degrees Kelvin is what we refer to when we talk about absolute zero. That is negative 406 degrees Fahrenheit or negative 273 degrees Celsius. As you can see on the graph, the moon at its very coldest is negative 280 degrees Fahrenheit or negative 170 degrees Celsius. And at that point, we're still at 100 degrees Kelvin. So Kelvin is really useful when we're dealing with temperature extremes. Okay, so that is it for talking about how the universe works. The next lecture will be dealing with the physical environment for life.